Hello and welcome to the AICE Chemistry Lecture Series. In this video, we're going to take a look at Chapter 14, Section 7, which is going to focus on the types of organic reactions and reaction mechanisms. Now, this is the title from the book, but in reality, we're mainly going to look at what reaction mechanisms are and how the different types of reactions happen. And then we'll look at types of organic reactions and how do we classify them in section 8. So let's get started. So reaction mechanisms, what are they? We use a series of steps in organic chemistry to show how a reaction happens. And that's what a reaction mechanism is. Essentially, the reaction mechanism is the how to the reaction, which is the what, right? So the reaction shows you what are the reactants, what are the products. The mechanism shows you how we get from the reactants to the products. So in reaction mechanisms, we're going to show things like the making and breaking of bonds. We're going to look at the series of steps that lead to a reaction happening. Sometimes it's one step, sometimes it's 2 or 3 steps. And with reaction mechanisms, one of the important things that we need to show is the flow of electrons, how electrons move, or otherwise the movement of electrons. In order to show the movement of electrons, what we do in reaction mechanisms is that we use curved arrows. Curved arrows are going to show electrons moving from point A to point B, either by breaking a bond, so whenever a bond is broken, electrons tend to move, or by forming bonds, so whenever electrons are used to create a bond, they're also going to have this curved arrow. Now, there's 2 important points whenever we're drawing a reaction mechanism that you will need to draw. Reaction mechanisms and their curved arrows, the curved arrows always need to start at electrons. That's going to mean that they're either going to start at a bond, so a line or a double bond or a triple bond, or a lone pair of electrons, because they show the movement of electrons. So the tail of the arrow, tail being the beginning part, needs to start at electrons, either a lone pair or in a bond. Now, depending on how many electrons are moving, we're going to use one of 2 arrows. The arrows can represent the movement of 2 electrons if they had a full head, meaning that the arrow has both parts to the head of the arrow, or the the curved arrow can show the movement of 1 electron if it has a half head, meaning that the other side of the arrowhead is not there. So we can see that in these 2 pictures here. As you can see in this reaction, or in this, really not reaction, but in this step, we see a chlorine molecule with 2 chlorines bonded to each other, and that chlorine is being broken. When that bond breaks, the 1 arrow with a half head is showing us a 1 electron from this bond, because remember that bonds are made out of 2 electrons, and hopefully we'll remember this from honors chemistry. A bond, or a single bond really, is made out of 2 electrons. So one of the electrons in that bond is going to the chlorine on the right, and that's why we see this curved arrow that shows a half head, and it starts at the bond. And then the other arrow here is showing us that the other electron in this bond, because there are 2, is going to the chlorine on the left. And again, because this has a half arrow, that means that 1 electron is being broken, or is being put over here. So this is how we show the breaking of a bond, right? How these 2 electrons are going somewhere other than the bond. So anytime we have a curved arrow starting at a bond, that usually shows the breaking of that bond and where the electrons from that bond go. On the other hand, if we have something like this on the right side, something like a bromide ion with its lone pair of electrons, if an arrow starts at a lone pair, generally speaking, that means that a bond is being formed. The formation of a bond, so the breaking of it. If it starts at the bond is being broken, if it starts at a lone pair, usually it means that it's being formed. And those electrons are being used to form a bond to this carbon over here. So we can see that both of the electrons in the lone pair are being used to create a bond because this arrow has a full head here. So that's showing us the whole 2 electrons, the whole lone pair, being used to create a bond. So we're going to see these arrows a lot in mechanisms. So start getting used to them because there's going to be a few different mechanisms that we look at throughout this curriculum for organic chemistry. Now don't worry about the other stuff like the positive carbon that's missing a bond or anything like that. We'll get into those details later on. But yeah, so these are how reaction mechanisms are shown. The reaction mechanism is the series of steps that show how a reaction happens, not reactants and products, but how do we get from the reactants to the products. And one of the most important things that they show is the movement of electrons by using curved arrows. If the curved arrow has a half head, then that means that's 1 electron being moved. If it has a full head, that means 2 electrons are being moved. And these arrows are always going to start at either a bond or a lone pair because they need to start at an electron. All right, so let's keep going. So what are some of the things that happen during chemical reactions? Well, again, we talked about how in a chemical mechanism or a reaction mechanism, bonds are either being formed or they're being broken. So let's talk about bond fission. Now, the word fission is just fancy chemistry term for breaking. Just like nuclear fission is a breaking of a nucleus, fission in chemistry and organic chemistry mechanisms, it means the breaking of a bond. Now, there are 2 types of ways in which a bond can be broken, either homolytic fission or heterolytic fission. So we'll start with homolytic fission and then move on to heterolytic fission in the next examples. What is homolytic fission? Well, the term, or the prefix, should I say, homo, means equal or same. Lytic, on the other hand, means breaking or lysis. So homolytic fission means equal breaking or same breaking. Equal breaking probably make more sense. During homolytic fission, the bond breaks evenly so that 1 electron from the pair of electrons in the bond goes to each atom that forms that bond. Meaning that, for example, if you have HCl, if that bond is broken homolytically, 1 electron from the bond goes to the hydrogen, and again we can tell that because of that half head on the arrow. So this represents the movement of 1 electron from the bond going through the hydrogen, and the other electron from the bond, and again we're going to put 1e here, the other electron from the bond going to the chlorine. That's how we know this is homolytic fission, because the bond is being equally broken to give 1 electron to each one of the atoms that forms that bond. Again, shown by the half head on the curved arrows. Now, homolytic fission leads to a very particular, very special type of compound, and we've used this vocab term way earlier in the year, but we are now going to actually apply it and see what they do. Homolytic fission is always going to lead to a creation of what we call free radicals, which are extremely reactive. Free radicals are atoms or molecules with unpaired electrons. Whenever this bond breaks homolytically, we're putting 1 electron on hydrogen and 1 electron on chlorine. Well, that leads to an odd number of valence electrons on these compounds, or these atoms in this case. Hydrogen has 1 valence electron, so that's a free radical. Chlorine has 7 valence electrons, so that's a free radical. So it is an atom or a molecule with an unpaired electron. That unpaired electron is extremely reactive. It's extremely unstable in chemistry in the atomic world. And so these free radicals are going to create reactions that create chain reactions because they don't want to exist. They want to react and therefore not be free radicals anymore. The homolytic fission is always going to lead to these free radicals because that bond being broken evenly means that these atoms are going to get one electron that is not paired up. Now, homolytic fission is always to lead to a type of reaction we call a free radical reaction. And we're going to look at this type of reaction later on in chapter 15, and specifically section 2 of chapter 15. And that's going to be the only free radical reaction we're going to see in the whole curriculum. But these free radical reactions all happen in the same way. They're going to happen with 3 steps. And they're a chain reaction, meaning that these 3 steps don't happen individually. It's not that step 1 happens, then step 2, then step 3. They all happen at the same time. Step 1 is going to happen, then step 2 is going to happen over and over and over and over and over again. And step 3 is going to end the reaction. But in reality, all 3 of these are happening continuously at the same time until there's enough of the step 3 for the reaction to stop happening altogether. Now, what are the 3 steps to a free radical reaction? The 3 steps to a free radical reaction are: number 1, initiation. Initiation is when the free radicals are created. Energy is going to be needed to break that bond. So initiation happens when a bond is broken homolytically, like we just said. And then the free radicals are created. That step requires energy because, like we saw earlier in the year in chapter 6, breaking bonds requires energy. Once that happens, once enough energy is given, and usually it's UV radiation, but we'll look at that in the next slide. Propagation can happen. What is propagation? Propagation happens when the free radicals react with molecules that are not free radicals. And what ends up happening is that they create a free radical on another molecule. So this is a chain reaction. Why? The initiation step creates the free radicals and requires energy, so that the step does not happen over and over and over again much because it requires a constant input of energy. But step 2, propagation, happens over and over and over again. Because once the free radicals are created, they react with molecules, and that reaction leads to the creation of free radicals and more molecules. Well, the free radicals created there react with more molecules, create more free radicals and more molecules. Those free radicals that get created go react with molecules and create more molecules. So it's a propagation step is a chain reaction that happens over and over and over again. It's a cycle. Once enough of that propagation step that happens, though, we can start to get what we call the termination step. Free radicals can react with each other to create a single molecule. Essentially the opposite of the initiation step. The free radicals react together and create molecules in the termination step. That's why it's called the termination step. It does not feed the chain reaction. It does not create more free radicals. So let's look at a few examples of these. Now, we're not going to look at the full reaction. This is not the full process of a free radical substitute or free radical reaction, because we're just interested in what each individual step looks like. Now, some of these are going to be from chapter 15, and I'm going to use that as an example. But realize that we're not looking at the specific chemicals that are created here. What we're going to focus on is what is happening. We'll look at the specific reaction in chapter 15. Now, like I said, propagation and termination both have different steps. This can happen in chain reactions, so there's actually a few different types of reactions that can happen. Propagation steps usually have 2 different reactions, and termination steps usually have 3. But we're not going to focus on that right now. We're going to just use one of each to show examples. So we saw the example of initiation already. The initiation step is pretty straightforward. We have a molecule that has a bond that is broken homolytically. That creates 2 free radicals. So in this initiation step, we're always going to get the creation of free radicals. That's always going to be the products of our initiation step, because they're needed. They're needed in order for the reaction to start happening because these are extremely reactive. So what happens? In the propagation step, those free radicals that are created that have an odd number of valence electrons, or they have unpaired valence electrons, and so they're usually just shown with one dot to represent that unpaired valence electron. Again, we discussed this earlier in the year, but chlorine here would have 2-3 other pairs of electrons. We're just not showing them because a lot of the time we don't show that in organic chemistry because these 3 pairs of electrons are not relevant to what's going on right now. Whereas that one unpaired electron is relevant because that's what makes this molecule so reactive. So we're not going to show those electrons. We're just going to show the one that we care about. Now in propagation, what happens is that these free radicals, which are extremely reactive, can react with other reactant molecules. When they do so, that one electron from the free radical is essentially going to steal an electron from one of the bonds in the molecule and create a bond to an atom in that molecule. So in this particular case, the chlorine free radical is using its one electron to create a bond to our hydrogen here in the methane molecule. Well, that's great. That gets rid of the chlorine free radical because that hydrogen and the chlorine form a bond by each putting in one electron. Again, notice that half head on the arrows. So the chlorine uses one electron to create a bond, to go into the bond. The hydrogen takes one electron from its bond with carbon to put into the bond. That creates our single bond and our HCl molecule. So this leads to the creation of a molecule and the chlorine free radical being gone. But the problem here is that when this happens, when the chlorine steals the hydrogen and the electron, the other electron in the bond is going to end up going to the carbon because this bond is essentially breaking homolytically. One electron goes to the carbon and creates this other molecule where the carbon has an unpaired electron. This is a free radical. So what do propagation steps do? They create free radicals and the molecule. So a propagation step is going to create a free radical and a molecule from a free radical and a molecule. Meaning that they don't actually solve any issues. They create a chain reaction. This free radical that we created is now able to go react with another molecule, create another free radical and a molecule. That free radical can go and react with another molecule, so on and so forth. That's why we call this a chain reaction. So the propagation step creates free radicals and a molecule from free radicals and a molecule. Finally, in the termination step is what ends the reaction, or what eventually ends the reaction as more and more molecules undergo the termination step. Termination steps happen when a free radical reacts with another free radical. So in this case, the free radical created during the initiation step meets a free radical created during the propagation step, because remember, these are all happening at the same time, and they react with each other. So the carbon, with its one electron that's unpaired, its free radical electron, reacts with chlorine that has its free radical electron, and they both put in those electrons to create a bond between the chlorine and the carbon. That bond creates a molecule out of these two compounds. So that bond that's created between carbon and chlorine using their lone free radical electrons, which is this one right here, creates a molecule. And that molecule cannot undergo any more chain reactions. And so eventually, once we have enough of these termination steps happening, the reaction just stops because there's no more free radicals. So those are the 3 steps to a free radical reaction. And we're going to look at the specific one in chapter 15 for halogen alkanes that creates a halogen alkane. But in chapter 15, we'll look at the specific one. For now, what we want to get out of this is that during the initiation step, a molecule undergoes homolytic fission, where the bond breaks evenly, each chlorine gets one electron, and it creates free radicals. During the propagation steps, free radicals are going to react with molecules to create more free radicals and more molecules, making a chain reaction, where this just keeps happening over and over again. And then as this propagation step goes, every now and then a few of these free radical molecules will find each other and undergo the termination step, where the free radical molecules react with each other and create a regular molecule. So that's usually what happens anytime we have homolytic fission happening, the breakage, the even breakage of a bond where each atom gets one electron. Now, that's not usually how things happen, though. Heterolytic fission is more common. Like I said, homolytic fission only happens in one reaction that we're going to see in chapter 15. But most of the time, we'll get what we call heterolytic fission. Heterolytic fission is the second kind of bond breakage. And again, remember, fission just means breaking. The prefix hetero means uneven or unequal. Meaning heterolytic fission is an unequal or uneven breaking. When heterolytic fission happens, when the bond breaks, the more electronegative element, and this is very important because if you ever wonder why we needed to know what electronegativity is and all that stuff, here's why. During heterolytic fission, the more electronegative atom takes both electrons from the bond. So this is an uneven breakage because one of the atoms, the more electronegative one, is going to take both of the electrons. So here we see that. If we have this, for example, chloromethane, to use the namings that we practiced already. If we have this chloromethane, when the carbon-chlorine bond breaks, because chlorine is more electronegative, those two electrons that are in that bond go to the chlorine. And we know this is two electrons, again, because that full head on the arrow. So that full head on the arrow tells us this is a movement of both electrons in the bond going to the chlorine. So what happens? When chlorine takes both of those electrons, it now has four lone pairs. Because remember, this chlorine, even though it's not being shown here, because a lot of the time we don't show it in organic chemistry, that chlorine has 3 lone pairs of electrons already. Once that 2 electrons from the bond go to a chlorine, we now have a chlorine with 4 lone pairs of electrons. And remember what we talked about earlier in this chapter, when an atom has more lone pairs than it's supposed to, like when this chlorine has 4 lone pairs instead of the 3 with one bond, it becomes negative. So this chlorine becomes a chloride ion when it breaks off. Whereas the carbon does not get any of the electrons from that bond. And so we have a carbon with 3 bonds and no lone pair. Whenever we have an element with no lone pair but a bond missing, remember that that element or that compound becomes positive in charge. So this creates a positive ion and a negative ion. And that's true of all heterolytic fission. Heterolytic fission is always going to lead to the creation of one cation, one positive ion, and one negative anion. In most organic molecules, this is going to lead to the creation of what we call a carbocation. A carbocation is an alkyl ion, and remember the term alkyl, and you're going to see this term before, or a lot, just means carbon chain or carbon containing. So a carbon chain, essentially a single bonded carbon chain. Single bonded. So a single bonded carbon chain, alkyl. So an alkyl ion is simply the ion form of a carbon chain, where the positive charge is on the carbon. So the carbocation, like the name implies, is a cation, a positive ion, on a carbon in an organic compound. So this will be a carbocation right here. Because we have that positive charge on the carbon in an organic compound. Carbocations are always going to have a carbon which is missing a bond, like in this case, this carbon right here. So heterolytic fission always leads to the creation of a cation, an anion, and because we're doing organic chemistry and everything has carbon, most of the time does not include a carbocation for the positive ion, a carbon with a positive charge. Now let's talk a little bit about those carbocations. Carbocations contain carbons which are electron deficient. And this is another word you will see a lot here. And I'm just trying to give you as much vocabulary as possible now so we're not confused later. So electron deficient, meaning that we are deficient of electrons. The word deficient meaning missing or low on. So electron deficient means a compound that is missing electrons, or that has less than 8 valence electrons. Usually, this means that we have 3 bonds and therefore a positive charge on electron deficient compounds. And so carbocations fit the bill pretty well. We have a carbon with a positive charge because it has 3 bonds, because that carbon does not have an 8 valence electrons. It has 6 valence electrons because of the missing bond. Now, there are 3 different types of carbocations. There are primary, secondary, and tertiary carbocations. And what these are based on is the number of R groups or alkyl groups, or essentially carbon chains, as we talked about in an earlier section, that are attached to the positive carbon. A primary carbocation, like the name implies, primary being 1, has 1 carbon chain or R group attached to the carbon. Secondary carbocations have 2 carbon chains attached to that positive carbon. And tertiary carbocations have 3 carbon chains attached to that positive carbon. So the term primary, secondary, or tertiary carbocation are just talking about how many carbon chains we have attached to this. So remember, R can be any number of carbon chains, right? So for a primary carbocation, we might have something like this. Actually, let me use a black screen for this. So for a primary carbocation, we might have something like C plus H2 C, let's say this. So this will be the carbocation of propane, because instead of having that hydrogen here at the end for propane, we'll have the positive ion. For a secondary carbocation, so let me change colors. For a secondary carbocation, we are going to have a, maybe, I'll keep using propane. C with a plus in the middle, and CH3 on one side, CH3 on the other. And this carbon needs a hydrogen to make it 3 bonds. And then for a tertiary carbocation, we might have that same structure with the CH3 on one side, CH3 on the other, but here instead of a hydrogen, we might have another carbon with 3 hydrogens. So why are they primary, secondary, tertiary? It's simply put because of the number of carbon chains. This carbon with a positive charge only has 1 carbon chain attached to it. That's our groups, right? The alkyl groups we talked about earlier. So that yellow right here, oops, I made that a little smaller. That yellow right here is our R group. It's a carbon chain. If we look at this one, the carbon with a positive charge has 2 different R groups here. We have R group number 1 on the left and 1 on the right. And this carbocation, which is tertiary, has 3. There's this right here. Oh, and I forgot the plus sign on that one. So, sorry about that. Although, you have 3 bonds, so you should know that this is the positive carbon right here. So we have here the carbon, the CH3 on the left, the CH3 on the right. Oh, it's not yellow anymore. CH3 on the right, and the CH3 on the bottom. So that's tertiary because it has 3 different R groups. Doesn't matter what that R group is. Doesn't matter if this is a 1 carbon chain, a 5 carbon chain, a 6 carbon chain. These R groups could be any number of carbons. But that what makes it tertiary, secondary, primary is not how many carbons in that chain, but how many carbon chains are attached to that positive carbon. So those are the different types of carbocations. So go back to our slide. So why is that important? And we're gonna see this take effect in a lot of the reactions we're gonna see later in the chapters. Why is this important? Since the carbons have a really low electronegativity, it's our electronegativity around 2.2, because they have such a low electronegativity, the alkyl groups, those carbon chains attached to a positive carbon, are what we call electron donating groups. Electron donating groups, when it comes to chemistry, are exactly what they sound like. They're compounds groups, or actually, let me say a different color there. They are groups of atoms with a functional group or a specific atom that have either low electronegativities, and so they can donate electrons, or whose electrons can be pulled away easily. And this is the case with carbon chains, right? They can be pulled away easily. Some electron donating groups we'll see later on are going to be groups where they can actually donate lone pairs of electrons. But when the case of an alkyl group, a carbon chain, there are groups where electrons can be pulled away easily. Why? Because that R group, that carbon chain, is made of carbon. And carbon has a very low electronegativity. That makes these alkyl groups, these R chains, electron donating, meaning the positive inductive effect can happen. Now, what is the positive inductive effect? And again, more vocabulary. This chapter is very heavy on the vocabulary. The carbocations are more stable when they have more alkyl groups. So a tertiary carbocation is most stable. Primary is the least stable, with the secondary in the middle. Why? These carbon groups, the R groups, are so low in electronegativity that when this carbocation forms, and we have this positive charge here, the electrons in their bonds get pulled towards the carbon. That's why we see these arrows right here. You see how those bonds have little arrows on them? That's to show, these little arrows right here are to show, and I'll circle on a different one here, that the electrons are being pulled towards the positive carbon. That's what the positive inductive effect is. Why does that happen? Well, very simple. This bond here is made out of 2 negative electrons. Those electrons are going to be attracted towards a positive carbon in the carbocation. So it's very straightforward in that sense. Now, what happens here is because we have negative electrons going towards that carbon, it's going to lower the charge density of that positive charge. Meaning that some of that positive charge, not the whole thing, but some of that positive charge is going to get neutralized by these electrons getting closer to it. And that means that because a positive charge is not as strong, it's less likely to react, making that tertiary carbocation more stable, because there's more inductive effect, positive inductive effect, than a primary carbocation. Because this primary carbocation only has these 2 electrons getting close to it, not the ones from the hydrogen bonds. And so that is going to not lower the charge density of this positive charge as much as it is here. So this positive charge essentially in this primary carbocation is stronger or higher than this positive charge, which is weaker. And it being weaker is actually a good thing because it makes it less likely to react, and so it makes it more stable. Whereas when you have a stronger positive charge in a carbocation, it makes it less stable because it's going to attract anything that is attracted to positive charges. So That's a bit of vocabulary. We have electron deficiency, we have carbocations, we have electron donating groups, and positive inductive effect. So if you want to re-listen to that explanation, back up the video a little bit, rewind, I would listen to it a couple times because these are important terms we're going to see. Speaking of important terms, the last topic we need to cover in this section is the difference between a nucleophile and an electrophile. And this is going to be very similar to the conversation we had about acids and bases earlier in the year, but it's going to revolve around organic reactions and organic mechanisms. So what is the difference between nucleophiles versus electrophiles? They're polar opposites of each other. They're exact opposites of each other. A few things I want to point out about the word before we get started. Phile usually means loving or attracted to, whereas the beginning of the word tells us what they're attracted to. So we have nucleo in nucleophiles and electro in electrophiles. So the easiest way to remember this is by remembering what these two words are related to. Nucleo is related to the nucleus, which is positive in charge. So nucleophiles are attracted to positive things, whereas electrophiles, electro should bring the term or the word electron to mind, meaning negative. So negatively charged. So a nucleophile is attracted to positively charged things. Electrophile is attracted to negatively charged things. So, and that's exactly what they are. A nucleophile is something that is attracted to positive charges because it's an electron-rich species, meaning that it is a compound or an atom that is electron-rich, has a lot of electrons, and it can donate those electrons. When a nucleophile donates the electrons, a pair of electrons, should I say, it forms a new covalent bond. So by the nucleophiles, what they're going to do, they're going to be attracted to electron or to positive things, donate a pair of electrons, forming, therefore, new covalent bonds. A lot of the time, nucleophiles are going to have either a negative charge or a partial negative charge because that comes from their extra electrons, from them being electron rich. So some examples of nucleophiles are things like the halide ions, chloride ions, bromide ions, because they have lots of lone pairs, they have a negative charge that makes them nucleophiles. On the other hand, electrophiles are going to be electron deficient species, meaning that they're missing electrons. And so they accept electron pairs. That's why they're attracted to negative charges. They're looking for electrons to accept. When an electrophile accepts an electron pair, they're going to form a new covalent bond. So nucleophiles donate electron pairs because they're electron rich to form new covalent bonds. Electrophiles are going to accept electron pairs because they're electron deficient to create a new covalent bond. Because they're electron deficient, a lot of times they'll have either positive or partial positive charges. So carbocations are a great example of an electrophile. And there are two sides of a coin, right? The nucleophiles are attracted to positive charges that the electrophiles have. They're going to donate electrons, while the electrophiles are going to accept electrons. And they're both creating bonds when they do that. So they're going to essentially react with each other. The electrophile, which is going to be positive or partially positively charged, is going to accept electrons, which we show by a curved arrow, from the nucleophile, which has extra electrons, electron lone pairs usually, and it has usually a negative charge. And they're going to create a new bond, shown here in black, when they do that, and forming a new molecule. So those are just terms that we use for the different components, different parts or molecules in an organic mechanism. That's it. That's the last set of vocabulary that we needed to go over. This is all the vocabulary we're going to need in order to look at the specific mechanisms, reaction mechanisms that we're going to see throughout this chapter. And in the next section, we'll just simply go over the different types of reactions that we're going to see these mechanisms for before we finish this chapter and move on to looking at particular functional groups. But that's it for section 7 of chapter 14. I will see you all in the next video.